Let's start. My name's Evan Sitt. I come from ADDITIVE University over in Budapest, Hungary. And our team, we decided to implement a digital synthesizer in functional programming. So as you can see, our team has a bunch of people there. Anyways, so I'll go over our motivation, background, briefly go over how we implemented the different main modules of our synthesizer, and then touch on our results, conclusion, and what we plan to do in the future. So our main motivation for doing this is that we teach a class at our university to our first semester students, bachelors. So these are people who've never touched programming before. So we want to, we teach them functional programming, and we want to give them something to show them that, hey, you're doing functional. It's not just for people in the master's program who do all these fancy conceptual type things. They're actual applications, things that you can do that you can have somewhat immediate results. So we decided to tackle applications that usually are done in C++ and Java frameworks, notably in this case digital synthesis, where the existing frameworks, there are some that exist such as Maximilian that's done in the UK. They're very excellent, but they're all done in C++. So we want to tackle them in functional because especially clean, but functional in general, so this can be done with any functional language. The abstractions that are offered, such as higher order functions, lazy evaluations, and algebraic data types, are particularly conducive to just doing digital signal processing. And also, when you look at the algorithms that a C++ framework uses, they're extremely efficient in terms of lowering the overhead for processing these things, but it's very hard to actually understand what's going on. And if you're, say, a musician type, like I was also, I still am, and you want to get into programming these things, or you want to customize, say, your own synth, so you want to make a sound that's unique to yourself, and you want to maybe customize it further, but then you look at the code and you go, what's going on, unless you're like, a programmer. So a big part of the motivation is that functional is really good for, this musical way of thinking, and we want to show that it can be done. So a little background first. I think everyone generally knows what digital synthesis is, because if you've listened to music in the last 30, 40 years, you've heard it. It started with these little keyboards. Some people here probably recognize that. And then after that, now everything's digital and software based, but they're all still basically digital representations of what you would actually have in terms of physical circuits. There are some differences because digital synthesis works with digital and discrete values versus an analog actual signal is continuous. And aside from this being a digital synthesizer for music, the application of this framework can also be used for anything that uses digital signal processing, such as music, but also telecommunications, for example. So one of the first modules that we implemented was one for wavetable lookup synthesis. Wavetable lookup synthesis, in a nutshell, is when you, instead of let's say you have a waveform and you want to compute it, you can tell your program to compute a sine value based on frequency and phase over and over again. But when you're running, say, 44,000 samples per second, and then you have to compute this either live or for a chunk of music that's 3 minutes, that's not particularly efficient to compute this over and over. So what we do is we do what's called wavetable. We pre-compute values, a certain set of values, and this set of values is based on our sampling rate. So in this case, for our specific project, we use the sampling rate of 44,100 hertz, and we accommodate the lowest human audible frequency of 20 hertz, so that we use a table of 2,000 values. After this, you use these values, so this is sort of a visualized way to see these values. We store them in something like, in our case, we use a constant time direct access array, so that when you access each value, you don't have to go through every single value. You can just go straight there. Now, why do we do this? Because it's actually very, very, very efficient. If you want to change a sound, say you want to change the frequency or phase of a sound, either set it at the beginning of your project or your workflow, or more commonly nowadays, you want to modify it live during your workflow, it's very easy to modify it. You just change where you access your array. So for the user, it's a waveform, but in the implementation, it's actually just a flat array, and you just change where you access it every now and then based on the values. And then if you want to prototype new features, it makes things easy, because all you have to do is you have this nice simple representation, implementation, and then if you want to implement anything else, like say an LFO, low frequency oscillator, envelopes, or any other effects, all you have to do is figure out how you want to play with these indices, which is just a bunch of math. And it's not really that complex of math either. And also, in the case that you want to improve your performance or quality, or you want to extend it to make it be able to do other things, you can also use interpolation methods. So in our project, we used just a linear interpolation, but you can easily extend this to use cubic, spline, or anything, so that you can improve the quality or even do some really weird, funky things with your sound, if you so choose to do. Then after you use the wavetable, so you have all these values, now what do you want to do with them? Generally, if you don't want just one waveform, because music isn't usually just one instrument, so you have a whole bunch of things, and that's where additive synthesis comes in. So for us, we use additive synthesis in two ways. The first is, in order to generate all of the waveforms, you can store all these different waveforms. So you can store a sine wave you can store a sine wave table, you can store a square wave table, you can store all these different ones, and there's unlimited numbers of different waveforms. However, that also requires a lot of storage. So instead, you can just use the Fourier series and break down all the other waveforms back down to the basic sines, and then build them back up using wavetable. And actually, this is pretty efficient. So with the Fourier series, the representation is we just have two arrays which represent the harmonics, and then the amplitudes, or rather the summation values of these harmonics. And each harmonic indicates an integer multiplication of your base frequency, which just changes how you sample the index, and then you sum them all up. So from there, you can have your harmonic. You can have one single sine wave table to generate all of your different sine waves. And as a side note here, the nice thing about using this method is that it also serves to appropriately change your digital discrete signals into an analog continuous signal. So in the case of a square wave or a pulse wave, you can't, in a digital world, you can go from -1 to 1 instantaneously. But in a physical world, you can't do that. That's physically impossible. So by doing this, you can actually appropriately make it work for an analog continuous signal. So once you do that, you can do a lot of fun things. So we used additive and subtractive synthesis to generate all these different waveforms. In this case, we have a triangle wave. So as you see, this is a triangle wave. So, and if you subtract it from itself, so you phase shift it a little bit, subtract it from itself, you get now a pulse wave. And that's now what's called pulse width modulation, PWM. It was pretty hot in the 80s. And then from there, then you can start doing a lot more fun things. So every time you synthesize a new waveform, whatever you want, you store that into a new waveform table. So, and then after you store that into a new waveform table, you recursively use that to add up and make more waveforms and store that again. And from there, so you can turn something that's just, you can start from a single sine wave table and very, very quickly make something that sounds more like a piano or something much more sophisticated by doing this. Additionally, not only is this very simple, it also makes it easy to optimize, because now you turn all this complicated synthesis, which in C++, I've looked at the algorithms, a hot mess, but in functional it's really nice because it's literally just addition and subtraction. And now you can optimize it however you like in the later, or you can just start changing the order of operations, or You can play with associativity and commutativity just if you want to. So then after we generate these waveforms, we want to start applying things to make our sound interesting, because then that's where the envelopes play in. So what envelopes are, they apply dampening and expansion, so you make it louder or quieter in sort of layman term, to your sound, and it gives it a different sound quality. So if, for example, here we see an ADSR profile, and depending on how you change it, you can have the same waveform sound like a guitar, or it can make it sound like a cello. And so in an example, in ADSR, we have 4 stages. We have the first stage, which is of the first step, which is the attack. So let's say you hit the key on your keyboard, you tell the sound to turn on. That's when it changes, okay, we're going to make it go up. Like it's going to get louder to however max loudness. Then it's going to take its time to decay. And then this is where you're holding the key out. So you sustain it. So let's say I hit the key, it's going to first jump and then sustain at a certain level. Now for a cello, it would have a longer attack, and it wouldn't have much of a decay, versus a guitar would have a really fast attack, decay quite a bit, and sustain at maybe half of the maximum. And then afterwards, you have the release tail, which is when you release how the sound decides to fade out. So with an envelope, you can take these already, you can take whatever sophisticated waveform you've made and then make even more types of synths based on that. So even between one, you can generate all of the string instruments just by changing your envelope. And envelopes are really easy to implement. So in our application, we started off with the basic 4-step ADSR, which is implemented everywhere. And then we extended it to the DA-HDSR, which has 6 steps, then an 8th step, and then finally we made an almost infinite step envelope, meaning that in our envelope, so this is just a 6-step, but in our multi-step, you can have as many steps as you want. You can have 9,000 steps if you want, and just tell it, okay, this is where attack starts, and this is where release starts, so on and so forth. And it's very flexible, and now at this point, if you're a musician and you want to have your sound do some really funky vibrato in the middle, okay, just use the multi-step, tell it, okay, just change it, or just tell it to generate the middle steps using a function, like a low-frequency oscillator. And so how do we get all these sound data? We use MIDI input. So because we want this application to work with everything that's actually already out there, we decided to use two sort of, global universal standards for input and output. So the 2 standards we used is MIDI for input and WAVE for output. So MIDI stands for Musical Instrument Digital Interface, and basically it's everything that's musical in terms of hardware and software nowadays use that. It's a lot smaller of a file than a WAVE because it doesn't contain audio data. It just contains a whole bunch of instructions that you have to read in. Now, one issue with MIDI is that because there are so many different types, it's been implemented back in the 70s, if I recall. Sometimes the MIDI instruction can be somewhat inconsistent, so you have to program it to work with that. But once you code this to work generally over any MIDI, your application can then be extended to accept any type of MIDI instruction. And nowadays, MIDI also controls things like you go to a show and you see pyrotechnics or fireworks or fog machines. Those are all controlled by MIDI. You can even, technically control the lights here to become a dance party with MIDI if you want. So it's pretty extendable. In terms of output, we use a PCM wave. So basically, anything you have now that puts out any sort of sound pretty much uses wave as their output. And we extend ours to support different bit rates, and we also can support any sampling rate. So with our results, what do we do? First, we decided to test with Fur-Elise because everyone knows Fur-Elise, and also because it's simple with monophonic, harmonic, and melodic lines. The first initial test took too long. It took 900 seconds to render. Then we utilized the power of functional to use unboxed arrays, and then it suddenly shrunk down to 3 seconds. And there's still room for additional optimization. And we even were able to render it with a reverb effect, and we're going to implement other effects such as flanger chorus. So basically what we figured is that, okay, the proof of concept worked. So musical paradigm works really well with functional. So whenever we were like, okay, we were able to implement this, let's try to extend it to meet these needs of what, say, a musician would want to do. Okay, we could put it in right away because music is very, as people would like to say, embarrassingly parallel. And the workflow actually works because you have an in and an out. It works very well with functional. We were able to prototype really fast. Once we made one feature work, we were like, okay, we made one time-based feature work, we can make the rest work. You make one frequency or volume-based, the rest can work really well. And then we also found that it works really well with a workflow like Scrum and Kanban. So in the future, we would like to extend this so that it can work better with outside applications, talk better formats, more filters and functionalities, and just make it eventually get to a point where we can convince people in the outside world, hey, try using something that's not C++ based. Okay, and that's it for now so that I don't run out of time too much. And if you guys have any questions, feel free to ask.